stared up at the vast night sky and wondered what secrets are hidden in the silent expanse? What mysteries are buried beneath our feet, waiting for us to uncover them? Think about this. A creature the size of a school bus, with a neck so long it could browse the tops of palm trees, once walked where your house now stands. Or imagine a monstrous feathered lizard with teeth like steak knives, whose footsteps would have shaken the very ground you're sleeping on. It's a history that's both bizarre and terrifying, yet so utterly fascinating. A true testament to the incredible resilience and inventiveness of life itself. We live on a planet that was, for over 160 million years, a kingdom ruled by these magnificent and often misunderstood animals. Their reign began quietly, in a world that would feel completely alien to us, and ended in an instant, in a flash of cosmic light. But their story isn't just about giant lizards and scary monsters. It's a saga of innovation, adaptation, and a world-shattering cataclysm. I'm glad you're here. Wishing you peace, rest, and maybe a little historical inspiration before sleep. Take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Let me know where you're listening from and what time it is for you in the comments below. And so, we go back in time, all the way to the late Triassic period, a time roughly 230 million years ago, a world that was still recovering from the largest mass extinction event in Earth's history. A world dominated by a single, sprawling supercontinent known as Pangaea, where the air was thick and humid, and strange, archaic reptiles and proto-mammals were the true power players. The first dinosaur wasn't a towering giant or a fearsome predator, but rather a small, lightly built creature, barely larger than a modern-day turkey, running on two legs through a landscape of ferns and primitive conifers. This little-known pioneer, a creature called Eoraptor, or maybe something even more primitive we haven't found yet, was a humble beginning for a dynasty that would last longer than the combined reigns of all the kings and queens in human history, an existence so long it makes our entire time on Earth seem like a fleeting blink of an eye. This dinosaur, or its close relative, was a biped, a choice of locomotion that offered it speed and agility, allowing it to navigate a world full of larger, slower competitors. A kind of biological underdog in an ecosystem ruled by fearsome crocodile-like archosaurs. And while we often picture a lush green world, the Pangaea of the late Triassic was, in many ways, a more arid seasonal place, with vast deserts stretching across its interior, broken up by coastal regions where life flourished. And it was in these more fertile regions that these early dinosaurs began to thrive, quietly carving out their own little niche in the shadow of the ruling class. We see this in the fossil record with the early sauropodomorphs, the ancestors of the long-necked giants we all know and love, starting out as modest bipedal herbivores, still figuring out the whole getting huge thing, and in the early theropods, who were already perfecting the art of hunting with sharp claws and powerful jaws. A curious scientific debate centers around the exact origin of dinosaurs. Was it a single, sudden evolutionary leap, or a more gradual, messy process with several dinosaur-like creatures evolving independently before the true lineage emerged? The truth is, we don't have a perfect fossil record for this exact moment, and that's part of the fun of paleontology, a continuous puzzle where every new bone fragment can completely change the picture we thought we had. These early dinosaurs, though not yet the kings of their world, were evolving with a certain efficiency, a kind of quiet biological momentum. Their upright posture, with legs tucked directly beneath their bodies instead of sprawling out to the sides like their reptilian cousins, was a game changer. It allowed for more efficient respiration, better endurance, and a faster gait, giving them a distinct advantage over their more lumbering rivals. And you can almost imagine them, these little guys, scampering through the undergrowth, dodging the big scary beasts of the time, patiently waiting for their moment. The Triassic period was truly a time of experimentation for life on Earth, a wild and woolly era where evolution was throwing everything at the wall to see what would stick, and it just so happened that the dinosaurs had the right combination of features to not only stick, but eventually take over. This slow and steady rise, from tiny two-legged creatures to the undisputed rulers of the land, is one of the most compelling stories in all of natural history, and it all started with a single, unpretentious step in the late Triassic. This slow burn of a beginning, however, was about to get a lot more interesting. As the Triassic marched on and these small, humble dinosaurs began to diversify, branching out into a dizzying array of forms. The first of these, and perhaps the most famous, were the sauropodomorphs, a group that started out innocently enough as small, two-legged herbivores like Brachiosaurus, but had a destiny to become the largest land animals to ever exist. Imagine a creature that in its early days was a gentle vegetarian, perhaps the size of a modern-day deer, but with a longer neck and tail, and a jaw full of small, leaf-shredding teeth. It would walk on its hind legs to reach higher foliage, but could drop down to all fours to graze. A kind of biological Swiss Army knife of a creature. This versatility was key to their success, and as the millennia rolled by, they began to scale up, getting bigger and bigger, their long necks allowing them to reach food sources that were completely inaccessible to their rivals. Meanwhile, a different lineage of dinosaurs, the theropods, were also finding their footing, but in a very different way. The earliest theropods were sleek, agile predators with sharp teeth and claws, built for speed and a quick takedown. Think of a creature like Colophysis, a famous early theropod from the American Southwest. It was a slender, delicate-looking animal, but don't let its size fool you. It was a formidable hunter, likely preying on smaller reptiles and other early dinosaurs, its powerful hind legs propelling it forward in a blur of motion. The sheer number of Colophysis fossils found in certain locations, like the Ghost Ranch Quarry in New Mexico, suggests they may have lived and hunted in groups, a fascinating glimpse into the early social lives of dinosaurs. The coexistence of these two groups, the herbivores and the carnivores, set up the classic predator-prey dynamic that would define the rest of the dinosaurian reign. It was a biological arms race, with herbivores evolving bigger bodies for defense and predators developing smarter hunting strategies to overcome their prey. And here we encounter a fascinating scientific mystery. Why did the sauropodomorphs evolve to such immense sizes? It's a question that has puzzled paleontologists for decades, and there's no single, easy answer. Some theories suggest it was a response to the arid conditions of Pangaea, where food might have been scarce and spread out, so a large body size would have allowed for a more efficient digestive system and the ability to go longer between meals. Other researchers believe it might have been a defense mechanism against the growing size of predatory theropods, with a larger body making them less of a target. Still others propose that a larger size was simply a side effect of a higher metabolic rate, a warm-blooded metabolism that required a massive body to regulate temperature. The truth is likely a combination of all these factors, a complex interplay of evolutionary pressures that pushed these gentle giants to their incredible scale. As the Triassic period drew to a close, the stage was set for a major shakeup. The world was still Pangaea, but the climate was becoming more seasonal, and the ecosystems were growing more complex. These early dinosaurs, the sauropodomorphs and theropods, were still just one group among many, sharing the world with all sorts of bizarre and wonderful creatures, from armored, crocodile-like phytosaurs to the long-necked, aquatic nothosaurs. They weren't yet the kings of the planet, but they were a growing force, a ticking time bomb of evolutionary potential. This was the moment before the storm, a quiet period of biological jockeying for position, and it's a good time to remember just how much competition there was. These early dinosaurs had to be tough, they had to be smart, and they had to be efficient just to survive, let alone thrive. Their legacy, however, was already being written in the rock layers, a slow-building masterpiece of evolutionary success that was about to be accelerated by a global catastrophe. So, let's just leave them there for a moment. These small, industrious dinosaurs, wandering across the vast landscape of Pangaea, unaware of the global event that was about to clear the way for their unprecedented dominance. And then, just as the dinosaurs were finding their footing, the world itself seemed to hit a reset button. Roughly 201 million years ago, at the boundary between the Triassic and Jurassic periods, a monumental extinction event occurred, a global catastrophe that completely reshaped the landscape of life on Earth. While not as famous as the one that would later end the dinosaurs' reign, this event was arguably more pivotal for them. It wasn't an asteroid impact, as far as we can tell, but rather a series of cataclysmic volcanic eruptions, a geological horror show that played out over hundreds of thousands of years. We call this the Central Atlantic Magmatic Province, or CAMP for short, and it was a period of immense volcanic activity as the supercontinent of Pangaea began to stretch and tear apart. Imagine a chain of volcanoes spewing forth enough molten rock to cover an area roughly the size of the continental United States, with rivers of lava flowing for miles, and the air filling with a suffocating mix of carbon dioxide and sulfur dioxide. This wasn't a sudden explosive event, but a slow, grinding apocalypse that systematically poisoned the atmosphere and destabilized the global climate. The consequences were dire for a vast number of creatures. The ocean ecosystem suffered a massive blow, with a significant percentage of marine species disappearing forever, likely due to ocean acidification and anoxia, a lack of oxygen in the water. On land, the ruling archosaurs, the fierce crocodile-like reptiles that had dominated the Triassic, were hit particularly hard. Their larger, more specialized bodies, which had been an advantage in a stable climate, became a liability in a world of wild temperature swings and toxic air. They simply couldn't adapt fast enough. The fossil record shows a dramatic drop-off in their numbers, a biological changing of the guard that was both swift and merciless. But the dinosaurs, those smaller, more adaptable creatures we were just talking about, seemed to weather the storm far better. Their smaller size and more efficient metabolism, a legacy of their bipedal ancestry, likely gave them an edge. They were more generalist, more flexible in what they could eat, and could move and migrate more easily in a changing world. It was a classic case of the little guys inheriting the earth. This extinction event is a great example of a scientific mystery still under active debate. While the volcanic activity of CAMP is widely accepted as the primary cause, the exact mechanism of how it led to such widespread extinction is still being studied. Was it the direct effect of volcanic gases, leading to a greenhouse effect and global warming? Or was it a more complex domino effect, where the initial warming led to a chain reaction of other ecological collapses? One of the most fascinating questions is why the dinosaurs were so resilient. Was it pure luck, or was there some inherent biological advantage they possessed? The answer likely lies in the intricate interplay of climate change, ecosystem dynamics, and simple evolutionary fortune. The Triassic-Jurassic extinction was the ultimate test for life on Earth, and the dinosaurs passed with flying colors. It was a tragedy for countless other species, but for the dinosaurs, it was a golden ticket, an open invitation to take over the planet. And that's exactly what they did. With their main competitors gone, the dinosaurs were free to expand, to diversify, and to grow to sizes previously unimaginable. The world of the Jurassic was a blank canvas, and the dinosaurs were about to paint a masterpiece. The ecological niches that had been vacated by the large archosaurs were now open for the taking, and the dinosaurs, with their unique biological blueprint, were perfectly positioned to fill them. It was a turning point in the history of life, a pivot from a world of reptilian diversity to a world defined by the Dinosaur Dynasty. The Triassic-Jurassic extinction was the moment the dinosaurs stopped being just another group of animals and started on their path to becoming the iconic giants we all know and love. It was a period of immense death and destruction, yes, but it was also the dawn of a new age, a Jurassic world ready for its new kings. With the slate wiped clean by the Triassic-Jurassic extinction event, the dinosaurs were free to truly flourish, and so began the magnificent Jurassic period, a time of unparalleled splendor and the true age of giants. The world was still Pangaea, but the cracks were beginning to show. The supercontinent was slowly rifting apart, creating new coastlines, new seas, and new climates, and the dinosaurs, now the undisputed rulers of the land, adapted and evolved to fill every available niche. This was the era that gave us the most iconic and recognizable dinosaurs, the colossal herbivores with necks so long they defied physics and the sleek, powerful predators that hunted them. Imagine a scene from the Jurassic, a herd of Brachiosaurus, their front legs longer than their back, like a living giraffe on a truly gargantuan scale, their heads held high, their gaze sweeping over a landscape of lush ferns and cycads, a kind of prehistoric botanical garden. Their sheer size was their defense, a testament to a world with abundant resources and a lack of competition. The sauropods, which had started as modest creatures in the Triassic, had exploded in size and diversity. Diplodocus, with its impossibly long whip-like tail, and Apatosaurus, the deceptive lizard, once famously mistaken for a different species, were all part of this magnificent parade. A fun little aside, the story of Apatosaurus being confused with Brontosaurus is a classic tale of paleontology, a scientific mix-up that captured the public's imagination and led to a whole lot of confusion for decades. The debate over whether Brontosaurus should be its own genus or simply a species of Apatosaurus is a classic example of how science is a continuous process of discovery and re-evaluation. Of course, a world full of giant herbivores needed equally impressive predators, and the Jurassic didn't disappoint. The theropods too had grown and diversified, with Allosaurus emerging as the quintessential large predator of the time. Think of a creature that was a masterpiece of carnivorous engineering, a powerful biped with serrated teeth, a jaw that could open incredibly wide, and an arsenal of sharp claws on its three-fingered hands. Allosaurus was the apex predator in many parts of the world, and it wasn't afraid to take on the biggest of the sauropods, possibly hunting in packs to bring down prey many times its size. The fossil evidence, particularly from sites like the Cleveland Lloyd Dinosaur Quarry in Utah, where a staggering number of Allosaurus skeletons have been found together, has led to a spirited debate. Were these a collection of predators who fell into a muddy death trap, or is this evidence of a communal hunting strategy? It's a great example of an open scientific mystery, a story told in bones that still has a few missing pages. And it wasn't just the big guys. The Jurassic was a time of immense evolutionary experimentation. The first feathered dinosaurs began to appear, hinting at the incredible future that awaited them. Stegosaurs, with their iconic plates and tail spikes, were a common sight. Their purpose still a matter of scholarly debate. Were the plates for thermal regulation, acting as solar panels to absorb heat or radiators to dissipate it? Or were they for display, a kind of billboard to attract mates or intimidate rivals? The scientific community leans toward a combination of these theories, with display being a strong contender due to the intricate patterns and shapes of the plates. The sheer variety of life in the Jurassic, from the tiniest feathered raptors to the biggest long-necked browsers, paints a picture of a world teeming with energy and life. The dinosaurs had arrived, and they were in complete command, a global empire of magnificent creatures stretching from pole to pole, a true golden age for a lineage that had started from such humble beginnings. The Jurassic was their moment, and they took it with a style and grandeur that has captivated our imaginations ever since. And of all the places on Earth that epitomize the Jurassic's grandeur, few compare to the Morrison Formation, a vast expanse of fossil-rich rock that stretches across the American West, painting a vivid and detailed portrait of a late Jurassic ecosystem. Think of it as a time capsule, a snapshot of a moment roughly 150 million years ago, where a massive semi-arid floodplain was crisscrossed by meandering rivers and dotted with large lakes. The climate was seasonal, with distinct wet and dry periods, creating a dynamic environment that supported an incredible diversity of life. This wasn't just a random collection of bones, it was a functioning community, a prehistoric drama playing out in real time, and we get to read the script, one fossil at a time. The Morrison Formation is a goldmine for paleontologists, giving us not only a peek at the individual animals, but a larger sense of how they all fit together in a complex, interwoven web of life. This is where many of the famous Jurassic dinosaurs we just talked about are found. It's the home of the sauropod giants like Apatosaurus, Diplodocus, and Brachiosaurus, which would have dwarfed any living land animal today, their long necks allowing them to browse on the tops of the conifer trees that dominated the landscape. You can almost picture them, like the world's most slow-motion parade, lumbering across the floodplain, leaving behind footprints the size of bathtubs. A fun fact for you, the sheer scale of some of these sauropods, particularly their tails, has led to a wild scientific hypothesis known as the sonic boom theory. Some researchers suggest that these long, whip-like tails could have been cracked like a bullwhip, creating a sound louder than a cannon shot, either for communication or to scare off predators. While it's a bit of a stretch and not widely accepted, it's a wonderfully imaginative idea that captures the sheer power of these animals. Of course, where there are giants, there are predators, and the Morrison Formation was home to the undisputed king of Jurassic carnivores, Allosaurus. This formidable theropod, a terror to the smaller dinosaurs and a threat to even the biggest sauropods, was likely the apex predator of the region. The ecosystem also included a variety of other theropods, like the smaller, more agile Coelurus, and even a few early tyrannosaurids, hinting at the future rulers of the Cretaceous. The herbivores weren't all giants either. This is the place where the iconic Stegosaurus roamed, its back adorned with those famous diamond-shaped plates and its tail tipped with lethal spikes, a walking testament to the variety of defensive strategies at play in the Jurassic. The Stegosaurus's brain, famously tiny for its body size, has been the subject of countless jokes, a sort of prehistoric punchline, but its incredible armor and tail spikes prove that you don't have to be a genius to be a survivor. And the Morrison Formation is also a treasure trove for open scientific mysteries, one of the biggest being the sheer number of different species of large sauropods living in the same area at the same time. How did they all coexist? How did a handful of different massive, long-necked herbivores manage to avoid direct competition for food? The leading hypothesis suggests a concept called niche partitioning, where each species specialized in eating different types of plants or browse at different heights, kind of like a team of specialized construction workers all building the same skyscraper, but with different jobs. Diplodocus, with its long horizontal neck, may have grazed on low-lying vegetation, while Brachiosaurus, with its upward-sloping body, could have reached the highest branches. This brilliant arrangement allowed for a kind of natural harmony, a delicate balance that kept the Morrison ecosystem thriving. It's a beautiful example of how nature, given the right circumstances, can find a way to support an astonishing amount of life. A majestic prehistoric tapestry woven from bone and stone. While the giants of the Jurassic were busy roaming the land, a quieter, yet arguably more important revolution was taking place in the evolutionary family tree, a story that would one day lead to the sparrows in your backyard and the eagles soaring high above. This was the evolution of feathers, a development that, for a long time, was seen as a uniquely avian trait. But as our understanding of dinosaurs has deepened, the line between dinosaur and bird has blurred into a beautifully complex tapestry. The first evidence of feathers in dinosaurs came from fossils of small theropods, the same lineage that gave us the fearsome T.rex, which seems a bit ironic, doesn't it? Imagine a little dinosaur, not much bigger than a crow, scurrying through the undergrowth with a downy coat, a kind of proto-feather. These weren't for flight at first. They were likely for insulation, helping these small, active creatures regulate their body temperature in a world of varying climates, much like a modern bird's fluffy down. The turning point in this story, the moment we truly understood the link, was the discovery of Archaeopteryx. This incredible creature, found in the Solnhofen limestone of Germany, is a famous transitional fossil, a kind of evolutionary bridge between non-avian dinosaurs and modern birds. It had a strange mix of features: the teeth, long bony tail, and clawed fingers of a dinosaur, but the unmistakable asymmetrical flight feathers of a bird. It was a mosaic of old and new, a living testament to the fact that evolution doesn't happen in a straight line, but in a series of small, often messy experiments. While Archaeopteryx could fly, it was likely a clumsy, uncoordinated flyer, more of a glider or a flutterer than a powerful aerial hunter. But it was a start, a first wobbly step into the sky that would lead to the aerodynamic marvels we see today. This discovery, along with many more since, has led to a fascinating and still unfolding scientific mystery. What was the exact evolutionary pathway from dinosaur to bird? The debate centers around a few key questions. Did the ability to fly evolve from the ground up, with a bipedal dinosaur using its arms to catch prey and then developing feathers to create lift? Or did it happen from the trees down, with a tree-dwelling dinosaur using its feathered arms to glide between branches, eventually leading to true flight? The fossil record suggests a variety of experiments, with different groups of dinosaurs developing different kinds of feathers and different anatomical features that could have led to flight. We have dinosaurs with long ribbon-like feathers, dinosaurs with 4 wings on their arms and legs, and a whole range of feathered creatures that probably never flew at all. This is a story of co-option, of a biological feature, feathers, that evolved for one purpose and was then repurposed for another. What started as a simple, insulating down coat eventually became a complex aerodynamic marvel, capable of lifting a creature into the air and allowing it to conquer a completely new domain. The existence of feathered dinosaurs completely reshaped our understanding of what a dinosaur was, transforming them from the scaly, lumbering beasts of our childhood imaginations into a vibrant, colorful, and surprisingly bird-like group of animals. Remember those sleek, agile theropods we talked about in the Triassic? Their descendants, in a few million years, would be taking to the skies, a final, beautiful act of a dynasty that was still in its golden age. The story of dinosaur feathers is a beautiful reminder that the line between past and present is not a sharp break, but a continuous living thread, a biological handshake between a tiny, feathered dinosaur and the bird on your windowsill. While some dinosaurs were experimenting with feathers in flight, others were taking a very different evolutionary path, one of armor and defense, a biological arms race that led to some of the most bizarre and beautiful creatures of the Jurassic. This is the story of the Stegosaurids, a group of herbivores defined by their iconic bony plates running down their backs and the lethal spikes on their tails. Think of the quintessential Stegosaurus, an animal that looks like a living puzzle, a creature so strange and distinctive that it's become one of the most beloved dinosaurs of all time. Its small head, low to the ground, and a posture that looks like it's perpetually grazing, belied a truly formidable defense system. The plates, known as osteoderms, were not connected to its skeleton, but were instead embedded in the skin, giving the dinosaur an almost armored, tiled appearance, a kind of natural mosaic. The purpose of these plates, those beautiful diamond-shaped structures, is a great example of a mainstream scientific fact that has been debated for a long, long time. For decades, the leading theory was that they were primarily for defense, a kind of bony shield to protect the animal from predators. But as we've learned more about the stegosaurid anatomy and the way these plates are arranged, that theory has become less likely. The plates themselves were surprisingly thin and riddled with blood vessels, making them a poor choice for a shield, and they didn't cover the sides of the animal, leaving it vulnerable to attack. A more recent, and now widely accepted theory is that the plates were for thermoregulation, a way for the animal to control its body temperature. Imagine the plates acting like a kind of radiator. In the cool morning, the dinosaur could orient its plates toward the sun to warm up, and in the heat of the midday sun, it could stand in the shade and use the plates to dissipate heat. This is supported by the intricate network of blood vessels we find in the fossils, suggesting a robust system for moving blood through the plates to either warm or cool the animal. But wait, there's a competing idea, another scholarly debate that adds a layer of fascinating complexity to the story. What if the plates were for display? What if they were a kind of billboard, a way for a stegosaur to signal its health, maturity, or even its species to potential mates or rivals? The large, elaborate plates of Stegosaurus would have been an unmistakable sign of a powerful, healthy animal, and the plates themselves varied in shape and size between different species, and even between individuals of the same species, which is exactly what we would expect if they were used for sexual selection. And you have to admit, those plates do make for a pretty striking silhouette, a kind of natural brand that screamed, "I'm a Stegosaurus, and I'm ready to mingle or rumble." It's a beautifully simple idea that could explain not only their function, but also their incredible variety. And then there are the tail spikes, the famous Thagomizer, a name coined as a joke in a comic strip that has now been adopted by paleontologists in a testament to their sense of humor. Unlike the plates, there is very little debate about the purpose of the Thagomizer. These four, long, sharp spikes were a lethal weapon, a powerful defense against predators like Allosaurus. The fossil record, in fact, includes an Allosaurus vertebra with a puncture wound that perfectly matches a Stegosaurus spike, a silent testimony to a violent confrontation that took place millions of years ago. It's a sobering reminder that for all their majesty, life in the Jurassic was a tough, often brutal affair. So, we can picture the Stegosaurus not as a slow, dumb creature, but as a heavily armed vegetarian, a walking fortress of plates and spikes, a silent, beautiful puzzle of an animal that mastered its environment through a combination of elegant defense and a little bit of prehistoric flair. As the Jurassic period drew to a close and the dinosaurs were at the height of their power, a new chapter was quietly unfolding, one that would completely transform the world's ecosystems and set the stage for a new wave of evolutionary innovation. This was the dawn of the Cretaceous period, a time that saw the final breakup of Pangaea, and perhaps most importantly, the rise of flowering plants. For millions of years, the world had been a green but somewhat monotonous place, dominated by non-flowering plants like ferns, cycads, and conifers, a kind of vast, prehistoric garden that lacked the vibrant colors and sweet scents we associate with modern flora. The dinosaurs of the Jurassic were perfectly adapted to this world. Their long necks and grinding teeth evolved to process tough, fibrous vegetation. But then, the angiosperms or flowering plants appeared and changed everything. It's a remarkable story of coevolution, a partnership between plants and animals that completely reshaped the landscape. Flowering plants, with their attractive blooms and delicious fruits, were a biological invitation to animals to come and participate in their reproduction. Insects, in particular, were drawn to the nectar and pollen, and as they moved from flower to flower, they inadvertently became messengers, carrying genetic material and helping the plants spread their seeds. This created a positive feedback loop. The plants that were better at attracting pollinators and dispersers were more successful, and the insects that were better at finding and utilizing these new food sources also thrived. It was a botanical and entomological revolution that led to a burst of new species and a level of ecological complexity the world had never seen before. This flowering revolution had a profound impact on the dinosaurs, a great example of a mainstream scientific fact that links botanical history to zoological history. The herbivores of the Cretaceous had a new and powerful food source, plants that were more nutritious and easier to digest than the old ferns and cycads. This led to a new wave of herbivores, dinosaurs with more specialized teeth and jaws, better equipped to handle a new menu. The duck-billed hadrosaurids, for instance, with their complex dental batteries, were perfectly suited for grinding down the tougher, more fibrous parts of flowering plants. A biological shredder on an industrial scale, the horned ceratopsians, with their powerful beaks, could snip and crop the new vegetation with precision. The old giants, the sauropods, continued to exist, but their dominance waned in some areas as the new herbivores took center stage. Of course, a new food source for the herbivores meant new opportunities for the carnivores. The Cretaceous period saw the rise of some of the most specialized and terrifying predators in dinosaur history, animals that were not only bigger but arguably smarter and more efficient hunters than their Jurassic predecessors. The Tyrannosaurids, which had started out as smaller, unassuming predators, were now on their way to becoming the apex predators of the world, a response to the growing size and number of their herbivorous prey. Fascinating ongoing scholarly debate centers on just how fast and widespread this angiosperm revolution was. Was it a slow, gradual takeover, or did flowering plants spread across the globe in a relatively short amount of time, radically altering ecosystems and causing a ripple effect throughout the food chain? The fossil record shows a dramatic increase in angiosperm pollen and leaves during the Cretaceous, but the exact timeline and impact on a global scale are still being pieced together. Regardless, the Cretaceous world was a place of vibrant colors, complex ecosystems, and a renewed evolutionary energy, a final magnificent act in the dinosaurian saga before the curtains closed. With the world now a vibrant mosaic of flowering plants and new herbivore species, the stage was set for the emergence of the final, and perhaps most famous, dynasty of predators to ever walk the earth, the Tyrannosaurids. The lineage had been around since the Jurassic, but they were initially small, unassuming carnivores, living in the shadow of the larger allosaurids. But in the Cretaceous, they had a growth spurt, a kind of biological glow-up that transformed them from also-rans into the undisputed rulers of their ecosystems. This wasn't just a matter of getting bigger, it was a fundamental shift in their anatomy and hunting strategy. The Tyrannosaurids became powerful, bone-crushing machines, a predator designed to take down the massive armored and horned herbivores that now populated the globe. And at the very end of this line, the grand finale, was Tyrannosaurus Rex, a name that literally means Tyrant Lizard King. This was the ultimate theropod, a creature so iconic it's become a household name, a symbol of brute strength and prehistoric terror. But the reality of T-Rex is far more complex and interesting than the one-dimensional monster we often see in movies. It was a massive animal, over 40 feet long and weighing up to 9 tons, with a skull that was a masterpiece of biological engineering. Its teeth, thick and serrated like a series of steak knives, were designed not just to slice but to crush, to deliver a killing bite that could shatter bone. The T-Rex had an immense bite force, one of the most powerful of any land animal ever discovered, a force so strong it could have probably crushed a car. This is a mainstream scientific fact that has been rigorously studied and confirmed through biomechanical modeling, a testament to the sheer power of this animal's jaws. And yet, despite its power, the T-Rex is at the center of one of the most famous open scientific mysteries in all of paleontology. Was it a hunter or a scavenger? This debate has raged for decades, with passionate arguments on both sides. Those who argue for scavenging point to its small, seemingly useless arms, which were too short to reach its mouth or even its own body. They suggest that an animal of that size would have needed to be an opportunist, an eater of carrion who used its enormous size and intimidating presence to scare off smaller predators from their kills. But those who argue for hunting point to its incredible binocular vision, a feature that would have been useless for a scavenger, but invaluable for a predator who needed to track and ambush prey. They also highlight its powerful legs, which suggest an animal built for running, even if not for a marathon. The truth, as is often the case, is likely somewhere in the middle. A large, powerful carnivore that was a fearsome hunter, but wouldn't turn down an easy meal if it found one. Think of a modern lion, a skilled hunter, but also not above scavenging from time to time. Another fascinating debate surrounds the appearance of T-Rex. We now have evidence that many theropods, including smaller relatives of T-Rex, had feathers, which leads to the scholarly debate. Did T-Rex have them too? While there's no definitive fossil evidence of feathers on T-Rex itself, it's a tantalizing possibility. Imagine a creature of that size, not with a scaly reptilian skin, but with a coat of downy proto-feathers, a kind of majestic feathered tyrant. It's a slightly comical, yet scientifically plausible image that completely upends our traditional view of this legendary dinosaur. Regardless of its exact appearance or hunting habits, T-Rex was the pinnacle of its lineage, the last and greatest of the theropods, a beautiful, terrifying, and utterly magnificent conclusion to the predator's tale. The tyrannosaurs may have been the top predators of the late Cretaceous, but the herbivores of the era were not defenseless. In fact, they evolved some of the most elaborate and formidable defensive structures in all of dinosaur history, a kind of biological castle with horns, frills, and a powerful shearing beak. This is the story of the ceratopsians, the horned faces, a group of dinosaurs that became incredibly diverse and successful, a testament to the evolutionary pressure exerted by the growing size and ferocity of their carnivorous foes. While the early ceratopsians were small, bipedal creatures, their later relatives, the ones we know and love, were gigantic four-legged tanks, a perfect example of a biological response to a changing world. Think of Triceratops, the most famous of this group, with its massive three-horned skull and a bony neck frill that could be over 6 feet across. This wasn't just a skull, it was a complex piece of engineering, a combination of weapons and armor that was a match for any predator, even a fully grown T-Rex. The two large brow horns, which could be over 3 feet long, were lethal weapons, capable of piercing the thick hide of an attacking predator, and the smaller horn on its nose was a powerful secondary defense. The massive frill, too, was more than just a shield. It was a kind of bony anchor for the powerful jaw muscles, giving the ceratopsian a shearing bite that could chop through tough, fibrous plants with ease. This combination of offense and defense made Triceratops a truly formidable creature, a walking fortress that was a perfect response to the new challenges of the Cretaceous. But what exactly was the purpose of that magnificent frill? This is another one of those great scholarly debates that shows how much we still have to learn. For a long time, the prevailing theory was that the frill was a giant shield, a protective plate to guard the neck and shoulders from a predator's attack. And while it certainly would have offered some protection, we know now that the frill was actually quite fragile in places, with large fenestrae, or openings, that would have made it a less than perfect shield. This has led to a competing theory that the frill was primarily for display. Imagine a herd of Triceratops facing off, not with their horns, but with their frills. A kind of prehistoric stare down where the biggest, most colorful frill won the day. The frills of different ceratopsian species are incredibly varied, from the simple, rounded frill of Triceratops to the more ornate, elaborate frills of creatures like Brachiosaurus, which had a series of long spikes radiating from its neck. This variety in form is a strong indicator that the frills were used for species recognition and sexual display, a kind of dinosaurian peacock tail. Of course, the horns had a similar dual purpose. They were undoubtedly used for defense against predators, a powerful deterrent to any hungry theropod. But they were also likely used for intraspecific combat, with males jousting for dominance or for the right to mate. The fossil record supports this idea, with some ceratopsian skulls showing evidence of horn wounds and healed fractures, a silent testimony to these ancient duels. So, the ceratopsians weren't just armored tanks. They were also masters of social signaling, using their magnificent headgear to communicate with each other in a world that was becoming increasingly complex. Their story is a beautiful example of how evolution can take a simple bone and, through a series of small incremental changes, turn it into a magnificent multi-purpose tool, a masterpiece of natural design that was both a weapon and a work of art. While the ceratopsians were busy building their horned fortresses, another group of herbivores was taking a different approach to defense, one of pure, unadulterated armor. This is the story of the ankylosaurids and nodosaurids, the armored tanks of the Cretaceous, a lineage that perfected the art of a low-slung, heavily protected body. Imagine a creature that looks like a living fortress, covered from head to tail in a mosaic of bony plates, a kind of biological chainmail that made them all but impervious to the attacks of even the most powerful predators. These were not fast animals, not agile hunters, but their defense was so effective that they didn't need to be. Their success was based on a simple, powerful idea. If you can't outrun them, out-armor them. The ankylosaurids, the more famous of the two groups, took this idea to its logical conclusion, adding a truly magnificent weapon to their arsenal, the bony tail club. Think of an animal like Ankylosaurus, with a wide, flat body covered in bony scutes, and a powerful low-slung tail, tipped with a massive club made of fused bone. This club was not for show. It was a lethal weapon, a kind of prehistoric mace that could be swung with incredible force. A direct hit to the legs of a predatory tyrannosaurid could have shattered its bones, leaving it crippled and vulnerable. The biomechanics of the ankylosaur tail club is a great example of a mainstream scientific fact that has been studied in detail, with researchers using computer models to calculate the force of a swing. The results are staggering, with the force of a full power swing easily capable of breaking bone. It was a perfect piece of defensive engineering, a response to a world where predators were getting bigger and stronger. But wait, there's a fascinating scientific mystery that still surrounds these animals. Why were their armored bodies so low to the ground? The debate centers on whether this was an adaptation for defense or a result of their feeding habits. Was it a defensive posture to make it harder for a predator to flip them over? Or was it a result of their specialized diet, with a low-slung body being better for grazing on the low-lying ferns and flowering plants of the Cretaceous? The truth is likely a combination of these factors. Their low body would have made them an incredibly difficult target for a predator to attack, with only their soft underbelly being vulnerable, and their wide, shovel-like snout was perfect for nipping and cropping plants close to the ground. It's a great example of how a single feature can have multiple evolutionary advantages. The nodosaurids, the other group of armored dinosaurs, took a slightly different approach. They were similar in body shape and armor, but they lacked the famous tail club. Instead, their defense was more passive, an incredibly robust, spiky armor that covered their entire bodies, often with long, sharp spikes protruding from their shoulders and sides. Think of a creature like Edmontonia, a walking fortress of bone and keratin. Their defense was simple, but effective. They were an armored pincushion, an unappetizing meal for even the most determined predator. This difference between the ankylosaurid's active defense, the tail club, and the nodosaurid's passive defense, the spikes, is a beautiful example of evolutionary variety. of two different ways to solve the same problem. These armored dinosaurs were not the brightest or the fastest, and they may not have been the most charismatic, but they were the ultimate survivors, a testament to the power of a good defense in a dangerous world. Their story is a quiet, powerful reminder that in the face of immense danger, sometimes the best defense is an impenetrable defense. While the ceratopsians and ankylosaurids were dominating the landscape with their powerful defenses, another group of herbivores was taking a completely different approach to success, one based on numbers, intelligence, and an incredibly specialized diet. This is the story of the hadrosaurids, the duck-billed dinosaurs, a lineage that became the most numerous and widespread large herbivores of the late Cretaceous. Imagine a creature that, at first glance, looks a bit like a gentle, oversized duck, but whose mouth held a secret weapon, a dental battery of hundreds of tightly packed teeth, a kind of biological shredder designed to process the toughest plants. The hadrosaurids were the ultimate grazers, the cows of the Cretaceous, and their success was a testament to the power of a good dental plan. A key to their dominance, and a great example of a mainstream scientific fact, was their unique skull and dental structure. Their snout, which did resemble a duck's bill, was actually a broad, horny beak that they used to snip and crop plants. But it was in the back of their mouth where the real magic happened. The dental battery was a series of grinding plates, with new teeth continuously growing in to replace the old worn-down ones, ensuring a constant supply of sharp, effective grinders. This allowed them to process a wide variety of tough, fibrous plants, including the new flowering plants that were beginning to dominate the landscape. They were also incredibly smart for a dinosaur, with a complex brain structure that hints at a more sophisticated social life. And this is where we get to one of the most fascinating scholarly debates surrounding these animals. What were those strange, hollow crests on their heads for? Think of a creature like Parasaurolophus, with its long, curved, bony tube extending from the back of its head. For a long time, paleontologists thought these crests were just for display, a kind of dinosaurian headdress to attract mates. But more recent research has shown that the crests were actually a complex series of tubes and passages that connected to their respiratory system. This led to the discovery that the crests were likely used for vocalization, a kind of natural trombone that could produce deep, resonant calls to communicate with other members of the herd. The shape and length of the crest varied between species and likely even between sexes, allowing for a wide variety of sounds, from a low-frequency rumble that could travel for miles to a higher-pitched call to warn of predators. This makes a lot of sense, as a creature that lived in large herds would need a way to communicate over long distances and distinguish between different individuals. And the evidence for their social lives doesn't stop there. Fossil sites have been found with vast numbers of hadrosaurid skeletons buried together, a kind of prehistoric mass grave that suggests they lived in large herds. We've also found fossilized nests with eggs and juveniles, a testament to their complex parental care. Think of a creature like Maiasaura, the good mother lizard, whose fossils were found alongside nests of its young, suggesting that it cared for its offspring long after they hatched. This evidence of herding, vocalization, and parental care paints a picture of a dinosaur that was far more sophisticated than we ever imagined. A social and intelligent creature that was a true master of its environment. The duck-billed dinosaurs were the quiet engine of the late Cretaceous ecosystem, a testament to the power of a successful, specialized niche, and a beautiful example of how nature rewards cooperation and communication as much as it does brute strength and aggression. Their story is a reminder that the most successful creatures are often not the biggest or the most terrifying, but the ones that are the most adaptable and the most connected. While the dinosaurs were busy dominating the land, a different kind of life was flourishing in the skies and seas, a parallel story of immense evolutionary success that played out alongside the Dinosaur Dynasty. These were the non-dinosaurian contemporaries, creatures that were not technically dinosaurs but shared the same world and often filled similar ecological roles. Imagine a world where the air was not filled with birds, but with pterosaurs, a kind of flying reptile with wings made of skin and muscle stretched between an elongated fourth finger in their body. And the oceans too were not home to whales and dolphins, but to a terrifying menagerie of marine reptiles, a diverse collection of predators that made the sea a dangerous but beautiful place. The story of the dinosaurs is often told in isolation, But to truly understand their world, you have to look at the full cast of characters. The Trosaurs in particular were a magnificent success story. They appeared in the late Triassic and lived all the way to the end of the Cretaceous, existing for longer than the dinosaurs themselves. They ranged in size from tiny, sparrow-sized creatures to truly immense giants like Quetzalcoatlus, a creature with a wingspan of over 30 feet, the largest animal ever to fly. These were not feathered creatures. Their wings were a masterpiece of biological engineering, with a complex system of muscles and fibers that allowed them to soar on air currents and hunt with incredible efficiency. This is a great example of an open scientific mystery. How did they get off the ground? An animal as large as Quetzalcoatlus would have had a hard time taking off from a standing start, and the leading theory is that they used their powerful front limbs to launch themselves into the air, a kind of quadrupedal takeoff that would have been a truly spectacular sight. It's a question that still sparks a lot of debate and new research, and the oceans too were full of incredible creatures. The ichthyosaurs, or fish lizards, were a group of marine reptiles that looked and acted a lot like modern dolphins and sharks, with streamlined bodies, powerful tails, and large eyes. They were fast, agile hunters, and their fossils show evidence of live birth, a sure sign of a fully marine lifestyle. Then there were the long-necked plesiosaurs, creatures that looked like a snake threaded through a turtle's body, and the fearsome mosasaurs, a group of giant marine lizards that appeared in the late Cretaceous and became the apex predators of the seas, a kind of dinosaurian sea monster with powerful jaws and a mouthful of sharp teeth. These were not dinosaurs, but they were the top predators of their ecosystems, a terrifying and beautiful parallel to the theropods on land. A fascinating scholarly debate surrounds the extinction of these creatures. While the pterosaurs and mosasaurs went extinct at the end of the Cretaceous, many ichthyosaurs and other marine reptiles had already died out long before, in a series of smaller extinction events. The question is why? Was it due to a changing climate, a shift in ocean currents and temperatures, or was it due to increased competition from other predators, like sharks and other fish that were also diversifying and growing in size? It's a complex puzzle with no easy answers, but it's a reminder that even when the dinosaurs were thriving, life was still a precarious and ever-changing game. The story of the pterosaurs and marine reptiles is a beautiful, if often overlooked, chapter in the history of the Mesozoic era, a testament to the incredible diversity of life that existed in a world that was truly and wonderfully strange. While the dinosaurs were busy evolving, the very ground beneath their feet was undergoing a transformation that was just as profound and just as important to their story. This is the story of continental drift, a slow but inexorable process that saw the supercontinent of Pangaea, the single landmass that had defined the Triassic and early Jurassic, begin to tear itself apart, creating the continents we know today. This wasn't a sudden, cataclysmic event, but a slow geological ballet that played out over millions of years, and its consequences for the dinosaurs were immense. A great example of a mainstream scientific fact that links geology directly to biology. As the continents separated, so too did the dinosaur populations on them, creating a kind of natural laboratory for evolution. The breakup of Pangaea began in earnest in the early Cretaceous, as a series of rifts opened up, first separating North America from Eurasia, and then South America and Africa from each other. As these land masses drifted apart, they carried their dinosaur populations with them, and those populations, now isolated from each other, began to evolve along different paths. This is a process known as allopatric speciation, and it led to an incredible burst of diversity. The dinosaurs of North America, for instance, began to look very different from their cousins in Europe or Asia, and the dinosaurs of South America and Africa, in particular, evolved in splendid isolation, creating some of the most unique and bizarre creatures of the Cretaceous. A great example of this is the difference between the theropods of the northern and southern continents. In the north, the Tyrannosaurs, which had started out small, were on their way to becoming the apex predators. But in the south, on the isolated land masses of South America and Africa, a different group of theropods, the abelisaurids, were the dominant carnivores. Think of a creature like Carnotaurus, a fearsome predator from South America with small, stubby arms and two horns over its eyes, a kind of dinosaurian devil. The abelisaurids evolved in a world without tyrannosaurids, and they became the masters of their own ecosystems. A beautiful example of how continental drift created separate evolutionary paths. This continental isolation also created a fascinating scholarly debate about a concept called island gigantism. As the land masses became smaller and more isolated, some creatures, particularly the herbivores, grew to immense sizes, a kind of biological response to a lack of predators. The sauropods, for instance, which had dominated the Jurassic, were still a presence in the Cretaceous, but in some of the smaller, more isolated continents, a new, dwarf species of sauropod appeared, a miniature version of the old giants. This contrast between the immense size of the northern sauropods and the smaller size of the southern ones is a testament to the power of a changing world, of a planet that was literally moving beneath their feet. The breakup of Pangaea also had a profound impact on global climate. As the continents separated, new ocean currents formed, and the global climate became more stable and more humid, leading to the proliferation of flowering plants and the lush, tropical world of the late Cretaceous. It's a reminder that the story of the dinosaurs is not just a story of animals, but a story of a planet, a living, breathing world that was constantly in flux. The global climate and the movement of the continents were not just a backdrop to the dinosaur story, they were active participants, shaping the evolution and distribution of life in a way that was both beautiful and terrifying. The story of continental drift is a silent, powerful thread that runs through the entire dinosaurian saga, a geological force that helped to both create and ultimately set the stage for their final, magnificent act. As the dinosaurs spread across a newly fractured planet, they weren't just evolving in size and defense, they were also becoming more complex in their social structures and behaviors. This is a quieter, but no less important chapter in their story, a glimpse into the heart of their lives as a species, and a great example of a mainstream scientific fact that has been gleaned from a careful reading of the fossil record. For a long time, we pictured dinosaurs as solitary, lumbering beasts, but that image is being replaced by a much more nuanced view of animals with complex social lives, with evidence of herding, nesting, and even a form of parental care. The key to unlocking this mystery has been the discovery of fossilized trackways and nesting sites, a kind of prehistoric photograph of a day in the life of a dinosaur. Fossilized trackways, for instance, tell us that many dinosaurs, particularly the large herbivores like sauropods and hadrosaurids, traveled in herds. Imagine a series of giant footprints, all moving in the same direction, with the tracks of smaller, younger animals nestled safely inside the tracks of the larger adults. This suggests a kind of protective herding behavior, a way for the adults to shield the young from predators, a kind of dinosaurian daycare on the move. The sheer size of some of these trackways, which can stretch for miles, is a testament to the immense size of these herds, a kind of walking, eating community that would have been a truly spectacular sight. And the evidence for nesting and parental care is even more compelling. The discovery of the famous Egg Mountain in Montana, a site with multiple fossilized nests of a hadrosaurid called Maiasaura, or good mother lizard, completely upended our understanding of dinosaur parenting. The nests were found in a large colony, much like a modern bird rookery, and they contained not just eggs but also juveniles that had already hatched and grown to a certain size. This suggests that the Maiasaura didn't just lay their eggs and leave them to fend for themselves. They stayed with their young, feeding and caring for them until they were old enough to leave the nest. This is a remarkable similarity to modern birds, a beautiful example of a behavior that was passed down from their dinosaurian ancestors. This is where we get into a fascinating, open scientific mystery. Were dinosaurs warm-blooded or cold-blooded? The discovery of parental care and complex social behaviors is a strong argument for warm-bloodedness. A creature that is warm-blooded or endothermic would have had a much higher metabolic rate and would have been able to sustain the energy needed to care for its young, to travel in herds, and to maintain a complex social structure. A cold-blooded or ectothermic animal would have been much more sluggish and less active, not the kind of creature that would be able to sustain a herd or care for its young for long periods of time. The bone structure of some dinosaurs also shows evidence of a high metabolic rate, with a dense network of blood vessels that is more typical of a warm-blooded animal. But there's a strong counter-argument, a scholarly debate that is still very much alive. A dinosaur the size of a sauropod would have had a massive body mass, and it would have been able to maintain a stable body temperature simply due to its size, a concept known as gigantothermy. It wouldn't have needed a high metabolic rate to stay warm. Its sheer bulk would have done the job for it. So, was it warm-blooded or not? The truth is likely somewhere in the middle, a kind of mesothermy, or a hybrid metabolism that was somewhere between a modern reptile and a modern mammal. Regardless, the evidence for their social lives and parental care paints a picture of a dinosaur that was far more sophisticated and complex than we ever gave it credit for. They were not just big, dumb lizards. They were social, caring, and surprisingly nurturing parents. A beautiful reminder that even in a world of giants, the bonds of family were just as important then as they are now. While the large herbivores were thriving in herds and the massive predators were ruling their domains, a different kind of dinosaur was quietly evolving in the shadows. A group of smaller, more agile theropods that were defined not by their brute strength, but by their intelligence. This is the story of the dromaeosaurids, the running lizards, and their close relatives, the troodontids, a group of dinosaurs that were likely the smartest of them all. A great example of an open scientific mystery that has been debated for decades. The dromaeosaurs, which include the famous Velociraptor and Deinonychus, were a force to be reckoned with, a kind of prehistoric special forces team that hunted in packs and used a unique weapon, a large retractable sickle-shaped claw on the second toe of each foot, a kind of dinosaurian switchblade. The intelligence of these creatures is not just a guess. It's a conclusion drawn from the fossil record, particularly from the size of their brains in relation to their body size. A creature like Troodon, a small slender theropod from the late Cretaceous, had the largest brain-to-body ratio of any dinosaur, an anatomical fact that suggests a level of intelligence and problem-solving ability that was well beyond that of the larger, more lumbering giants. It had large eyes, which hint at a crepuscular or low-light hunting style, and its teeth were serrated on both sides, a unique feature that suggests it was a versatile hunter, capable of taking down a wide variety of prey. The discovery of Troodon completely changed our understanding of dinosaur intelligence, forcing us to reevaluate our long-held view of them as simple-minded reptiles. And the dromaeosaurids, too, were likely a lot smarter than we once thought. While the image of a pack of highly intelligent, coordinated velociraptors from the movies is a bit of an exaggeration, there is some evidence to suggest that they were social hunters. The discovery of multiple Deinonychus skeletons alongside the remains of a larger herbivore, Tyrannosaurus, is a strong indication that they were pack hunters, a kind of prehistoric wolf pack that worked together to bring down prey many times their size. The fact that they were able to take down such large animals when they themselves are not particularly big is a testament to their intelligence and their ability to cooperate, a kind of social strategy that was a powerful evolutionary tool. This brings us to a fascinating scholarly debate. What exactly were those sickle claws used for? The popular image is that they were used to slash and disembowel prey, a kind of grisly weapon of mass destruction. But more recent research, using biomechanical modeling and a better understanding of their anatomy, has suggested a different use. The claws were not particularly sharp, and they were more likely used to pin down struggling prey, to hold onto a target while the pack delivered the killing bite with their powerful jaws. Think of it more as a grappling hook than a knife, a tool for subduing prey rather than tearing it apart. It's a subtle but important distinction that paints a picture of a more nuanced, and perhaps even more terrifying, predator, a creature that used its intelligence and its tools to overcome its prey in a strategic, rather than a purely brutal way. The story of the dromaeosaurids and troodontids is a beautiful reminder that in the world of dinosaurs, brains were just as important as brawn, and that the quiet, clever hunters were just as successful as the loud, powerful giants. They were the perfect hunters for a world that was becoming more complex, and their success was a testament to the power of a keen mind and a sharp eye. As the dinosaurs reached the zenith of their reign, an entirely different kind of cataclysm was unfolding far away, on the other side of the planet, a geological event that would prove to be a quiet harbinger of the end. This is the story of the Deccan Traps, a massive volcanic province in what is now modern-day India, a great example of a mainstream scientific fact that has become a key player in the dinosaur extinction debate. For hundreds of thousands of years, leading up to the very end of the Cretaceous, A series of immense volcanic eruptions spewed forth an almost unimaginable amount of lava, covering an area of over 500,000 square kilometers. This wasn't a single explosive event, but a series of continuous grinding eruptions that systematically poisoned the global climate. The scale of this volcanism is hard to comprehend. Imagine a series of eruptions that lasted for thousands of generations, with rivers of molten rock flowing across the landscape and a constant, suffocating cloud of sulfur dioxide and carbon dioxide pouring into the atmosphere. The effects were global. The sulfur dioxide would have reacted with water vapor to form a kind of sulfuric acid haze, which would have cooled the planet by blocking out sunlight, a kind of volcanic winter. But the carbon dioxide, a powerful greenhouse gas, would have eventually led to global warming, a kind of 1-2 punch that completely destabilized the global climate. This is a crucial piece of the puzzle, a kind of environmental stress test that the world was undergoing right before the final, more famous event. And this leads us to a fascinating, open scientific mystery. What was the exact role of the Deccan traps in the dinosaur extinction? For a long time, the volcanism was considered the primary cause of the extinction, a slow-motion catastrophe that simply made the world uninhabitable for the large, specialized dinosaurs. But with the discovery of the Chicxulub impact crater, the volcanism was relegated to a secondary, supporting role, a kind of background noise to the main event. Now, however, the debate has re-emerged, with some scientists arguing that the volcanism was the real killer, a gradual extinction event that was simply accelerated by the asteroid impact. They point to the fact that the extinctions were not instantaneous, that many groups of dinosaurs were already in decline before the impact, and that the volcanism could have been the final straw. This is a great scholarly debate, a kind of historical whodunit with two primary suspects. Was it the sudden, violent impact of an asteroid that wiped out the dinosaurs in a single fiery flash? Or was it the slow, grinding death of a planet suffocated by volcanic gases? The truth, as is often the case, is likely a combination of both. The Deccan traps would have already stressed the global ecosystems, making them more fragile and more vulnerable to a major shock. The asteroid impact, then, was not the sole cause, but the final lethal blow to a world that was already on the brink. The volcanism had already thinned the herd, making the final extinction event more effective and more devastating. So, as we approach the final moments of the dinosaurian saga, it's important to remember that the seeds of their demise were already being sown, not by a celestial rock, but by the very ground beneath their feet, a silent, powerful force that was a harbinger of the end. The Deccan traps were a kind of geological curtain call, a slow-motion reminder that even a dynasty that had lasted for 160 million years was not immune to the forces of a changing world. So, the stage was set, the world was already stressed and on the brink, and then, from the silent, endless darkness of space, came the final cataclysmic blow. This is the story of the Chicxulub impact, a world-shattering event that, in a single moment, brought the 160 million year reign of the dinosaurs to a fiery, dramatic end. Imagine a rock, a cosmic wanderer, maybe 6 miles wide, hurtling through the atmosphere at a speed of over 40,000 miles per hour, a kind of unstoppable bullet aimed directly at a lush, tropical world. It was a collision of unimaginable power, a force of nature that changed the course of life on Earth forever, a great example of a mainstream scientific fact that has been confirmed by decades of geological and paleontological research. The evidence for this impact is overwhelming. At the boundary between the Cretaceous and Paleogene periods, a geological layer known as the KPG boundary, we find a thin worldwide layer of iridium, an element that is incredibly rare on Earth's surface but common in asteroids. This iridium layer is a kind of geological fingerprint, a signature of a cosmic impact that was global in scale. We also find shocked quartz, a form of quartz that has been deformed by the immense pressure of an impact, and tektites, small glass-like spherules that were formed from molten rock being blasted into the atmosphere and then raining back down on the planet. And the smoking gun, the final piece of the puzzle, is the Chicxulub crater itself, a massive 110-mile-wide impact crater buried beneath the Yucatan Peninsula in Mexico, a silent, powerful scar on the face of the Earth that is a testament to the sheer power of the collision. The immediate consequences of this impact were nothing short of apocalyptic. The asteroid struck with the force of billions of nuclear bombs, creating an instantaneous flash of light that would have been brighter than 1,000 suns, and a shockwave that would have leveled everything in its path for hundreds of miles. The impact vaporized an immense amount of rock, blasting it into the atmosphere and creating a massive fireball that would have incinerated everything in its vicinity. But that was just the beginning. The impact also created a series of tsunamis, with waves hundreds of feet high, that would have scoured the coastlines of North and South America, a kind of watery death that added to the immediate devastation. The energy of the impact also sparked a global firestorm, with trees and plants igniting all over the world, a kind of worldwide barbecue that incinerated much of the remaining life. But this is where we get into a fascinating open scientific mystery. How did this one event, this single, instantaneous moment, lead to such a massive, worldwide extinction? The death toll from the initial impact was certainly high, but it wasn't enough to explain the complete disappearance of the dinosaurs. The answer lies in the long-term effects, the aftermath of the impact that plunged the world into a kind of global winter. The dust and soot from the impact, combined with the sulfur dioxide from the vaporized rock, created a thick, dark cloud that encircled the globe, blocking out the sun and plunging the world into a kind of perpetual night. This is a great scholarly debate, a kind of historical mystery that has a few missing pages. Was it the soot from the global firestorm? Or was it the sulfur dioxide from the vaporized rock? The most recent research suggests it was a combination of both, a deadly mix that blocked out the sun and plunged the world into a deep freeze. Regardless of the exact mechanism, the result was the same. The world was plunged into darkness, and the end was coming. The asteroid impact was not a quiet end, but a violent, instantaneous moment of pure, unadulterated chaos that was the beginning of the end for the Dinosaur Dynasty. The moment the cosmic bullet slammed into the shallow seas of the Yucatan Peninsula, it sent a shockwave rippling through the very fabric of the planet, a seismic tremor that would have been felt around the globe, an earth-shattering event of a magnitude that we can barely comprehend. The immediate devastation was localized but horrific, a kind of ground zero of annihilation, a great example of a mainstream scientific fact that has been reconstructed from geological evidence and computer models. The impact vaporized an immense amount of rock, including a significant amount of sulfur and other volatile elements, and blasted it all into the atmosphere, a kind of geological gunshot that sent a massive plume of superheated material rocketing into the sky, a kind of fiery cloud that would have been visible from space. And it was this plume that created the most immediate and perhaps most terrifying consequence, a global firestorm. As the vaporized rock and other debris re-entered the atmosphere, it created a kind of planetary oven, with the air temperature rising to hundreds of degrees, a heat so intense that it would have ignited every flammable object on Earth. Think of a world where the sky itself is a weapon, a kind of radiant heat that would have incinerated forests, grasslands, and anything else in its path. We find evidence of this in the form of a global soot layer at the KPG boundary, a thick black layer of ash that is a silent testimony to a worldwide barbecue. This firestorm would have been a quick, brutal end for many creatures, a kind of instant cremation for a vast number of animals, both on land and in the sea. But that was just the beginning of the long, slow, grinding apocalypse. This is where we get into a fascinating, open scientific mystery. How did some creatures survive this initial firestorm? Was it because they were in a cave or burrow, a kind of underground bunker that protected them from the heat? Or was it because they were aquatic, living in a medium that would have insulated them from the searing heat of the atmosphere? The answer is likely a combination of these factors, a kind of biological lottery, where the winners were the ones who happened to be in the right place at the right time. The small mammals, for instance, which were burrowing creatures, were perfectly positioned to survive the initial blast, a kind of natural immunity to a very unnatural event. The crocodiles and turtles, too, which could submerge themselves in the water, were able to weather the storm, a kind of aquatic sanctuary from the fires above. It's a great example of how a species' pre-existing traits can become a life-saving advantage in a crisis. And of course, the asteroid impact also created a series of monstrous tsunamis, with waves hundreds of feet high that would have scoured the coastlines of North and South America. The fossil record from this time is full of evidence of this, with jumbled piles of bones and other debris, a kind of geological junk pile that is a silent testimony to a watery death. But the fires and the tsunamis, for all their horror, were just the overture to the main event. They were the immediate, localized effects of a global disaster, a kind of first wave of destruction. The real killer, the one that would systematically dismantle the entire dinosaurian world, was yet to come. The initial impact was a kind of punctuation mark, a sudden, violent end to a sentence that had been a long time in the making. The world had been irrevocably changed, and the long, dark, cold days of the global winter were about to begin, a kind of biological reckoning that would spell the end for a dynasty that had reigned supreme for over 160 million years. The initial flash and firestorm were just the beginning, a dramatic opening act for a much longer and more insidious catastrophe. This is the story of the global winter and the subsequent ecological collapse, a great example of a mainstream scientific fact that has been painstakingly reconstructed from a variety of geological and paleontological evidence. As the dust and soot from the impact and the global firestorm were blasted into the atmosphere, they didn't just disappear, they created a thick, dark cloud that encircled the entire planet, a kind of perpetual shroud that blocked out the sun and plunged the world into a deep, sustained cold. This wasn't a seasonal change. It was a global blackout that lasted for months, maybe even years, and it was the real killer for a vast number of species. Imagine a world where the sun, the ultimate source of all life's energy, is gone. The plants, which rely on photosynthesis to grow, would have died off almost immediately, a kind of botanical mass extinction that would have been devastating to the herbivores that relied on them for food. The small, quick-growing plants might have survived in some isolated pockets, but the large, slow-growing conifers and flowering plants that had been the backbone of the Cretaceous ecosystem would have vanished, a kind of botanical purge that left the world a barren and lifeless place. And of course, with the plants gone, the herbivores would have starved, and with the herbivores gone, the carnivores would have starved, a kind of domino effect that systematically dismantled the entire food chain from the bottom up. This is a classic case of ecological collapse, a great example of how a single event can have a ripple effect that touches every part of an ecosystem. And this is where we encounter a fascinating, open scientific mystery. How cold did it get? The models suggest a dramatic drop in global temperatures, a kind of deep freeze that would have been catastrophic for the large, warm-blooded dinosaurs. But the exact temperature drop and the length of the global winter are still a matter of debate. Some models suggest a drop of over 50 degrees Fahrenheit, a kind of super freeze that would have made the polar regions of the planet uninhabitable. Others suggest a more moderate drop, but one that was still enough to kill off the vast majority of plant life. The truth is likely somewhere in the middle, a deep freeze that, when combined with the lack of sunlight and the collapse of the food chain, was enough to seal the fate of the dinosaurs. And the collapse wasn't just on land. The oceans, too, were hit hard. The lack of sunlight would have killed off the phytoplankton, the tiny photosynthesizing organisms that are the base of the marine food chain. With the phytoplankton gone, the small creatures that fed on them would have starved, and with those creatures gone, the larger marine reptiles would have starved, a kind of aquatic version of the land-based ecological collapse. The ammonites, a group of shelled cephalopods that had been a staple of the marine diet for millions of years, were completely wiped out, a kind of quiet, but no less significant, extinction that was a testament to the global reach of the disaster. The world had gone dark, it had gone cold, and for the dinosaurs, it was game over. The long, magnificent reign of the Dinosaur Dynasty was over, not with a bang, but with a whimper, a kind of slow, grinding death that was a terrible, but fitting, end to a story that had lasted for over 160 million years. The stage was now set for a new kind of life, a new kind of animal, to emerge from the darkness. In the wake of the global winter, the world was a shattered, barren place, a kind of post-apocalyptic landscape that was utterly unrecognizable from the lush, vibrant world that had existed just a short time before. But amidst the death and destruction, a few creatures, a handful of survivors, were able to cling to life. A great example of a mainstream scientific fact that has been pieced together from a careful study of the fossil record. These were not the large, specialized dinosaurs that had dominated the planet for so long, but smaller, more adaptable creatures, a kind of biological remnant that would one day inherit the Earth. Their survival was a testament to a combination of luck and pre-existing traits that, in a crisis, became a life-saving advantage. The first group of survivors, and perhaps the most important for our own story, were the small burrowing mammals. These creatures, which had lived in the shadows of the dinosaurs for over 160 million years, were perfectly positioned to survive the initial impact and the subsequent global winter. They were small, so they didn't need a lot of food, and their burrowing lifestyle gave them a natural immunity to the searing heat of the global firestorm. They were also likely omnivores, with a varied diet that allowed them to eat a wide variety of things, from seeds and roots to the carcasses of the dead, a kind of opportunistic feeding strategy that was a powerful advantage in a world where food was scarce. Their small size and adaptability were a kind of biological insurance policy, a set of traits that, in a world-ending event, were the key to their survival. The second group of survivors, and the one that is a direct link to the Dinosaur Dynasty, were the birds. While all of the large non-avian dinosaurs were wiped out, a small lineage of avian dinosaurs, the ancestors of modern birds, were able to cling to life. The debate over why they survived is a fascinating open scientific mystery, a kind of scholarly whodunit with a few different suspects. Some scientists argue that it was their small size that allowed them to survive, a kind of small is beautiful theory, where their lower metabolic rate and lower food requirements gave them an edge. Others argue that it was their ability to fly, which would have allowed them to escape the immediate devastation and find food in new, untouched areas. Still others point to their high metabolic rate and warm-bloodedness, which would have given them the ability to survive in a cold world where other animals were freezing to death. The truth is likely a combination of these factors, a kind of perfect storm of survival traits that allowed them to weather a storm that killed everything else. And of course, there were the other survivors, the crocodiles, turtles, and other cold-blooded reptiles that were able to survive by slowing down their metabolism and waiting for the long winter to end. They were able to enter a kind of hibernation, a state of suspended animation that allowed them to survive without food for long periods of time. They were also able to submerge themselves in the water, which would have protected them from the firestorm and the initial blast. Their survival is a great example of a different kind of survival strategy, one based not on speed and intelligence, but on a kind of biological resilience, a slow, patient approach to a world that was in chaos. So, as the dust settled and the world slowly began to emerge from the darkness, it was not the dinosaurs who were there to greet the dawn, but a strange and wonderful new collection of creatures, a kind of biological cast of characters that had, against all odds, survived the end of the world. The survival of some creatures and the complete extinction of others remains one of the most compelling mysteries in all of paleontology, a question that gets to the very heart of the end Cretaceous extinction. It's not just about the dinosaurs, but about the entire ecosystem, and why certain groups were able to weather a storm that wiped out so much of life on Earth. Why did the crocodiles and turtles survive, but the massive marine reptiles like mosasaurs did not? Why did the small burrowing mammals inherit the Earth, while their larger, more specialized counterparts perished? The answer, a great example of an open scientific mystery that is still being debated, is likely a combination of several factors, a kind of perfect storm of survival traits that gave some creatures an edge, while others were simply out of luck. One of the leading scholarly debates centers on the size matters hypothesis. The vast majority of creatures that went extinct were large, with a body mass of over 25 kilograms. These large animals would have needed a lot of food, and in a world where the plant life had been wiped out by the global winter, they simply starved to death. The small animals, on the other hand, with their lower metabolic rates and lower food requirements, were able to survive on the dwindling food sources, a kind of biological minimalism that was a powerful advantage in a world of scarcity. The fact that the largest surviving land animal was the crocodile, a creature that can go for months without food, is a strong argument for this hypothesis. It was a kind of biological purge, where the large specialized creatures were systematically eliminated, and the small generalist creatures were left to inherit the Earth. Another key part of the puzzle is the dietary niche hypothesis. The extinction event was particularly hard on herbivores, as the plant life was the first to go. The large, specialized herbivores, with their finely tuned digestive systems, were completely out of luck, but the omnivores and scavengers, with their more varied diet, were able to survive on the carcasses of the dead and the small surviving plant life. The small mammals, for instance, which were likely omnivores, were able to eat a wide variety of things, a kind of opportunistic feeding strategy that was a powerful advantage. The birds, too, with their ability to fly and find food in new, untouched areas, were able to survive, a kind of biological mobility that was a great advantage in a world of chaos. It's a classic case of the generalists inheriting the earth, a kind of biological lesson that in a world of uncertainty, it's better to be a jack of all trades than a master of one. And finally, there's the location matters hypothesis. The asteroid impact was not a global, uniform event, but a localized disaster with global consequences. The creatures that were in the right place at the right time, like the burrowing mammals that were protected from the initial blast, were more likely to survive. The creatures that were in the wrong place, like the large specialized dinosaurs that were out in the open, were completely out of luck. It's a kind of biological lottery, where survival was not just a matter of fitness, but also a matter of fortune. The end of the Cretaceous was not a clean, neat event, but a messy, chaotic, and often random affair, where the winners were not necessarily the best or the brightest, but the ones that happened to be in the right place at the right time. The story of why some creatures survived is a beautiful, if often cruel reminder that in a world of chaos, survival is not just a matter of strength, but a matter of luck, resilience, and a little bit of opportunistic genius. As the global winter began to fade and the world slowly emerged from the darkness, a new era was dawning, a kind of biological spring that would see the rise of a new dynasty. With the large specialized dinosaurs gone, the ecological niches that they had occupied were now wide open, a kind of biological vacuum just waiting to be filled. A great example of a mainstream scientific fact known as adaptive radiation. This is the story of the rapid evolution and diversification of the mammals, a group of creatures that had spent over 160 million years living in the shadows of the dinosaurs, but who were now, in the Paleogene period, the undisputed masters of the land. They had survived by being small, adaptable, and generalist, and now they were ready to take over. The first few million years after the extinction event saw an explosion of mammalian diversity. The small, shrew-like mammals that had survived the extinction began to evolve into a dizzying array of forms, a kind of evolutionary arms race to fill every available niche. We see this in the fossil record with the appearance of new and bizarre creatures, from the first primitive primates to the ancestors of modern horses and rhinos, all of them evolving at a pace that was unimaginable during the long, slow reign of the dinosaurs. The world, which had been a kind of botanical and zoological desert, was now a land of opportunity, and the mammals were taking full advantage of it. They were no longer the underdogs, they were the new kings. And this leads us to a fascinating open scientific mystery. Why did the mammals get so big, so fast? For 160 million years, they had been small. And then, in a geological blink of an eye, they were getting to the size of rhinos and elephants. The debate centers on whether this was a direct result of the extinction of the dinosaurs, a kind of biological response to a lack of competition, or whether it was a more complex process involving a changing global climate. Some scientists argue that the absence of the large predatory dinosaurs allowed the mammals to grow to larger sizes without being hunted, a kind of biological get-out-of-jail-free card. Others argue that the changing global climate, which was becoming more humid and tropical in the early Paleogene, provided a new, abundant food source that allowed for larger body sizes. The truth is likely a combination of both, a kind of perfect storm of opportunity and environmental change that allowed the mammals to take over in a way that was both swift and decisive. The rise of the mammals also saw the diversification of a completely new kind of ecosystem. The flowering plants, which had survived the extinction in isolated pockets, began to spread and diversify, creating new food sources and new habitats that the mammals were perfectly positioned to exploit. The first grasses, for instance, which are a cornerstone of modern ecosystems, began to appear, creating vast open grasslands that were home to herds of grazing mammals. The world was no longer the deep, dark forests of the Jurassic, but a diverse and vibrant tapestry of ecosystems, from the open plains to the dense tropical jungles, and the mammals were the ones who were there to enjoy it. The story of the rise of the mammals is a beautiful, if often overlooked, chapter in the history of life on Earth, a testament to the power of adaptability and resilience, and a powerful reminder that even in the face of a world-ending catastrophe, life, in all its forms, always finds a way to survive and to thrive. In the aftermath of the Great Extinction, the world was no longer a realm of giants. It was a world inherited by the small, the quick, and the adaptable. But to say the dinosaurs were gone is not entirely accurate. In fact, a small but vital part of their lineage survived, and they are with us today. A great example of a mainstream scientific fact that has completely redefined our understanding of both dinosaurs and birds. This is the story of the legacy of the dinosaurs, a story that is not a tale of a dynasty that died, but a tale of one that simply evolved and took to the skies, a kind of airborne resurrection that has been a long time in the making. The connection between birds and dinosaurs is one of the most stunning discoveries in all of paleontology. We now know that birds are not just related to dinosaurs. They are, in fact, avian dinosaurs, a living lineage of a group that we thought was long dead. This is supported by a staggering amount of evidence, from the anatomical similarities between birds and small feathered theropods to the presence of features like wishbones, hollow bones, and three-toed feet that are found in both. A creature like Velociraptor or Troodon is in many ways just a flightless bird, a kind of dinosaurian cousin that never quite got off the ground. The anatomical similarities are so striking that many paleontologists now consider the distinction between birds and dinosaurs to be a kind of artificial construct, a remnant of a time when we didn't understand the full scope of their connection. This brings us to a fascinating open scientific mystery. Why did only one lineage of dinosaurs survive the extinction event? Why did the non-avian dinosaurs perish, while the birds, which were also dinosaurs, were able to cling to life? This is a scholarly debate that is still very much alive, with a few different theories vying for the top spot. One theory suggests that it was their small size and their ability to fly that gave them the edge. They were able to escape the immediate devastation, find food in new, untouched areas, and their small size meant they didn't need a lot of food to survive the long global winter. Another theory suggests that it was their diet. The birds that survived were likely granivores, or seed eaters, and the seeds of the surviving plants would have been a powerful food source in a world where everything else had died. A third theory points to their ability to lay eggs, a reproductive strategy that would have allowed them to reproduce quickly and repopulate the world once the long winter had ended. The truth is likely a combination of these factors, a kind of biological toolkit that gave them a powerful advantage in a world of chaos. And so, we see the legacy of the dinosaurs every day, in the birds that we see in our backyards, in the majestic eagles that soar high above, and in the chickens that we eat for dinner. These are not just birds, they are living dinosaurs, a kind of biological time capsule that connects us directly to the world of the Mesozoic. The story of their survival is a beautiful reminder that a dynasty that reigned for over 160 million years did not just disappear. It simply changed form, a kind of airborne evolution that allowed a small part of their lineage to live on and to thrive in a world that was no longer theirs. The dinosaurs are not gone. They are just different, a testament to the incredible power of life to adapt, to evolve, and to survive, no matter what the world throws at it. So, the next time you see a bird, take a moment to appreciate it, for you're looking at a living, breathing dinosaur, a quiet but powerful reminder of a dynasty that was once the undisputed ruler of the world. And so, we come to the end of our story, a saga that began in the silent supercontinent world of the late Triassic and ended in a flash of cosmic light at the close of the Cretaceous. It's a story of a dynasty that reigned for over 160 million years, a testament to the incredible resilience and inventiveness of life itself. We've seen them rise from humble, turkey-sized beginnings to become the colossal giants of the Jurassic and the fearsome predators of the Cretaceous. We've watched them evolve a dizzying array of forms, from the heavily armored tanks of the ankylosaurids to the magnificent horned faces of the ceratopsians, and we've discovered a secret life of herding, parenting, and intelligence that completely upends our traditional view of them as big, dumb lizards. And in the end, we watched them fall, not in a quiet decline, but in a sudden, violent cataclysm that plunged the world into a darkness from which only a few would emerge. But the story doesn't end there. The dinosaurs didn't just disappear, they simply changed form. In the humble, feathered creatures that survived the Great Extinction, we find a living, breathing link to that long-lost world, a powerful reminder that the past is not gone, but is instead a living part of the present. The birds we see today are the direct descendants of a small lineage of dinosaurs, a quiet, beautiful coda to a story of immense power and grandeur. Their survival is a testament to the fact that evolution is not a race, but a continuous living thread, a biological handshake between a tiny feathered dinosaur and the bird on your windowsill. As we end this journey, let's take a moment to reflect on the sheer scale of their existence, our own time on Earth, the entire history of our species, from the first hominids to the sprawling technological world we live in today, is but a fleeting blink of an eye in the grand, long saga of the dinosaurs. They were the undisputed rulers of the world for a period of time so vast it's almost incomprehensible, and their story is a powerful reminder that our time here is a brief, but beautiful, moment in a much larger, much older story. We are not the first dynasty to rule this planet, and we may not be the last, and there is a kind of humbling comfort in that thought. And so, as the final images of the Cretaceous world fade, and we're left with the silent, dark echoes of a long-lost time, I want you to close your eyes and imagine it one last time. The immense sauropods, their long necks swaying in the wind, the fearsome T.rex with its thunderous footfalls, and the beautiful feathered creatures that would one day take to the skies. It's a world that is both strange and familiar, a world that is now just a collection of bones and fossils, but a world that, for a long, long time, was the only one that mattered. And in that thought, there is a kind of quiet beauty, a sense of wonder that can only come from contemplating a world that was, for a time, so completely and so wonderfully different from our own. So, rest now and let the long, quiet sleep of the dinosaurs come to you, for their time is over, but their story lives on, a silent, powerful whisper that can still be heard if you listen closely enough.